Okay. Yep.
Also, do I have a pointer or a clicker, or do I just have to hit the space bar? So I just have to.
If you have to point to something, maybe you can
just do this. Okay.
Marker.
Well, I like to just kind of.
Okay.
Here.
Right. And remember to bring the clicker and pointer next.
Okay. So we're recording?
Yeah.
All right. So without further ado, and now it's not doing it. Oh, there it goes.
Okay. Maybe you can go to full screen. Maybe
There we go.
that's better. Yeah.
There we go. Oh, so there's the about me. We can just skip on ahead. All right. So what is light trapping? Let's start with just the broad philosophical overview of what we're trying to talk about here. So it's pretty straightforward. It's exactly what it sounds like. You have some thing in space and a bunch of light is hitting it, and some of that light might just miss it entirely, or it might bounce off the surface and reflect away. Some of it might even go inside and bounce around, eventually scatter out the opposite end. And depending on the properties of whatever your thingamajig is here, some of it will be absorbed and turn into maybe heat or electron-hole recombination or splitting, that kind of thing. And that's the fundamental thing we're interested in, is how much of that energy impingent on my object of interest. Some fraction of that's going to be absorbed in it in some way, and the rest will either just scatter away, bounce away, or transmit through out the other end. So this word, we can define to quantify that as the light trapping efficiency, or some people call it an absorption factor, and it's just the ratio of all that energy that gets absorbed in the thing to the total amount of energy striking it. If you like to think of it more in quantum mechanical terms, you can think of it as, here is a photon. A single photon comes into this area, and what is the probability of that photon getting absorbed in it versus scattering away and passing through? Same idea, and we're going to sort of just treat the classical perspective and the quantum perspective interchangeably. So hopefully that won't get very confusing, but that's just kind of how optics is at the end of the day. So what are some applications for light trapping? So maybe one obvious application is the classic stealth bomber perspective of you've got some plane and radar waves are hitting it, and you don't want any of those signals to go back and reflect away towards the transmitter and be detected. So that's where they talk about that special paint that they put on these airplanes to absorb all that energy that hits them. The anechoic chamber, you can think of as kind of a special application where you have all these magical cones along the wall designed to minimize reflection, to just absorb all the energy that hits them so that nothing bounces back and interferes with your measurement over here. And of course, we're going to update some installations here. There you go, thank you. And then, but this is optics for energy, so we're going to focus primarily on solar cells. But it's just kind of important to think in the back of your mind that all these ideas have maybe some broader applications depending on how you look at them. So let's start with the big picture. This is a fun graphic I always kind of like to begin with. So it shows just the continental United States plus Hawaii and Alaska here. And what you're seeing is the photovoltaic solar resource. So this is just the total light droppings on the United States. We'll kind of ignore Alaska and Hawaii for now, just focus on the continental here. And you notice the units down here on the colored bar are kilowatt hours per square meter per day. And I think it's just sort of, I'm not sure if this is peak or if it's averaged over the year, because it just says annual average. There you go. Yeah, so it's not, so depending on summer, this might be more and winter will be less. And we just kind of average it all out. And so, of course, Arizona and New Mexico is this big, giant, barren desert, so they have tons and tons of sunlight out here. And, of course, you get up here and they're like Maine, and it's all green. It's like maybe half the energy almost. Alaska is really, not so much at all. So I think if you do, I haven't done the actual math in a while, but I think if you just kind of take my thumb and put a little blotch there, if you were to just like fill my fingernail with solar cells there and add up all the energy hitting it, that would be about enough to supply like either the entire United States energy demand plus extra for the world. It's like a huge amount going over a tiny little area in principle. And then you look here at the graphic on the left, you notice that solar cells are a thing. We've built them. We've got solar farms here and there around the world. And so if there's so much energy available and the technology exists, why aren't we just flooding the Arizona desert right now with solar cells and just supplying all of our energy needs from now until forever? So this is sort of a broad philosophical question I like to ask, like what's the holdup? Why aren't we doing this? So just spitball some answers for me. Give me 6. Politics is a good one, because global warming is a giant Chinese conspiracy, and so we don't have to do it. We can just burn coal to our heart's content, right? But eventually we're going to run out of fossil fuel. Maybe not today, but at least a few hundred years or so. It's going to get progressively more and more difficult to mine this stuff. So we could transport ourselves 200 years in the future, and we burned up all the oil and coal there is, and this will be a problem again. So what will be some limitations, though? Other limitations you can think about. Yeah.
Solar cells don't convert 100% of the energy.
That's another good point. So just because the sun is dropping 7 kilowatt hours per square meter per day, there's some finite fraction of that you can actually convert. So maybe when I say my pinky here, what I really mean is like my entire hand. So we'll explore some of the fundamental limits on that efficiency in the upcoming slides. So that's a good question. What are some other problems you can think of? How about if I have a house here in Maine, how am I supposed to collect energy that's generated here in Arizona or Texas or Florida? So just the problem of transmitting energy is a giant problem of infrastructure as well. So maybe at the very least we'll supply everybody here and we'll kind of gradually transmit the energy that way. But that's a big problem, is just getting the energy from here to there. What's another problem maybe you can think of?
Light usage.
Nighttime. This is an average, right? So when it's nighttime, we're not actually generating energy in the night. So you have to store energy at some point, right? So that's a big area of research right now, what to do with all that energy, because maybe I'll build a giant solar farm and I'm making all this energy during the day, and then somehow I have to store it and continue to provide energy into the night.
No one's at cost yet.
Cost is another big problem, because solar cells aren't cheap and coal is, and some of these things are more or less subsidized than others. So I don't know the specifics on all that, but
eventually when the coal, when the amount of coal is being produced, one day the price of coal will go higher than
one day, but is that day today? So that's a barrier for us
also,
today.
already we use coal for making solar panels, so it just adds up the cost for solar panels.
Yes, it takes energy to make energy, right? The expression, you've got to spend money to make money. You have to spend energy to make energy. So do we even come out ahead in our energy budget? So some finite amount of energy has to go into making the solar cell, and this solar cell has a finite lifetime, which it can use to produce energy. And if it takes more energy than it creates, that can be a problem as well. So definitely the longevity of the solar cell is a big deal. So you can see it's complicated. Just because the energy is there doesn't mean we can just start flooding the desert with solar cells and gobbling it all up. Ideally, we like to push in that direction, but there's obviously a lot of obstacles there, which is why solar cells have been just this amazingly hot topic in research for the last couple of decades. So cost was a big deal. So when I was doing my PhD, I was back in around 2008 to 2010. You see how the module, what is ASP? I forget what that represents. I think it's, does it say anywhere? Oh crap, I forgot what that stands for. But it's just the total sort of accumulated price to build a solar panel, say. So you notice it's in units of, they even inflation adjust. So it's $2,016 per watt. So this is a big push back in around 2012, was to try and bring the cost of an integrated solar cell down to $1 per watt, which is this bar here. And that was kind of universally regarded as the threshold where you don't have to necessarily subsidize this stuff anymore, and the market will just take over and start building these things on its own. Yeah, what's up?
Does that mean $2016 per watt?
Yes.
Okay, not $2016.
Right. So
a year,
it's an inflation adjustment, right? Because obviously, dollars meant something different back in 1990 than they did today. So it's all just kind of a market adjustment and inflation adjustment. So we had actually kind of started hitting the target back in 2016, 2017. We beat the dollar per watt goal. So that was pretty cool. Kind of neat to see that happen, because I remember back in 2010, 2011, it was not really certain whether or not we would meet it, but there was this huge push by the Department of Energy. Dollar per watt is kind of the magic number. And in recent years, we've seen a lot of check out, yeah, so you can see cumulative global shipments in terms of megawatts. So you see as the cost goes down, the shipments of actual solar cell production has been going way, way up, which is a very nice thing to see.
Yeah, so is that dollar per megawatt? You're saying dollar per watt?
Dollar per watt is the word. So if you want to generate a megawatt facility, it would cost you $1 million to build it. That's the, or if you have a 5 kilowatts of power generation on your home, then presumably you have to invest $5,000 to get that. Okay. So the main point though is as price goes down, production goes up, and so you can see there's time is sort of just indicated at certain points here on this graph, which is kind of interesting. So we're seeing, I guess you could think of it as this golden age or renaissance in solar cell production and installation around the country, and hopefully, fingers crossed, we'll just keep seeing production increase even more. You notice this is a logarithmic scale too, 1,000, 10,000, 100,000, a million here. So 1 million megawatts is almost the gigawatt scale, and I think the total annual U.S. energy consumption is measured in terawatts. So I haven't looked that up recently, but it's way up there. So if we're getting into the gigawatt scale of production, that's when we start reaching a significant fraction of our total energy demand. So there's lots of barriers, but they are slowly but surely being overcome. So this is now a light trapping lecture. So we're going to focus on the anatomy of a solar cell and why light trapping is important and how we can maximize it and use it to our advantages. So you begin with just the very crudest representation of a solar cell, which is a p-n junction with a top metal contact and a bottom contact, and light just sort of raining in from above. So you imagine photons just trickling in like rain, and some of them maybe bounce off away, but some of them get into your solar cell, and by sheer luck, eventually that photon will bang into an electron and create an electron-hole pair. So you get the hole here will just sort of meander around. With any luck, it eventually runs into the bottom contact, and the electron will then do its little Brownian walk and eventually reach a top contact. And when those guys separate, that is energy that you can then harvest in the form of a photocurrent. So what do you make the solar cell out of? So this is a big question that determines a lot of the industrial applications and profitability and long-term environmental conditions. You have to pick a material to make the solar cell, and not all materials are created equally. So one of my professors used to joke that technically, in principle, you could go out into the street and grab a lump of tar and concrete, and if you're very good with your chemistry and semiconductor physics, you could, in principle, create a solar cell out of that. It wouldn't necessarily be a very good one, but the physics is there, and you can make solar cells out of all sorts of materials around the world. So for a while, the leading solar cell production was this company called First Solar. And they were using cadmium telluride to make solar cells. And they were the first guys to beat the dollar per watt target, incidentally. But you can't do cadmium telluride forever for a number of reasons. Like the first is because cadmium and tellurium aren't exactly abundant materials in the Earth's crust, and they're actually what's called secondary metals. So you don't just like find an ore deposit of cadmium and start mining it for the cadmium and the tellurium. Really what would happen is you mine copper, and cadmium and tellurium are just secondary metals that just kind of trickle off out of the process while you're going after the copper. So that meant there was only kind of a finite supply of the materials by which they could make their solar cells. So it was nice that they beat the dollar per watt, but it's the sort of thing where just physically isn't enough atoms of that stuff in the Earth's crust to really create gigawatt scale or terawatt scale infrastructure. So for that reason, silicon tends to be the primary material of choice when making solar cells. If you take enough classes, you'll know there's like indium gallium phosphide solar cells and a bunch of others I can't remember off the top of my head, but they exist. So silicon is kind of the go-to material for a number. So first and foremost, it's abundant. It's pretty much the most abundant element in Earth's crust. So it's not like we're really going to run out of this stuff anytime soon. It's not exactly the most toxic stuff in the world because it's really refined dirt when you think about it. So which means if you chop them all up and throw them in a landfill, you're not going to be poisoning any groundwaters like you would if you were dumping a bunch of heavy metals. So that's very appealing. It's relatively easy to process. There's this huge infrastructure. So from like the 50s and on, ever since we had the big semiconductor industry to make computer processors, we've had this huge industry dedicated to figure out how to make silicon do really interesting things. So we already kind of knew in advance all the physics of silicon anyway, and didn't have to reinvent any wheels with other materials. And incidentally, just by a wild coincidence, the band gap of silicon happens to be pretty close to the ideal value given our sun. So we'll talk about those limits in a little bit. So whenever you go and buy a solar cell off of Amazon or off the shelf, odds are it'll be made out of silicon in some form or another. So you notice it's the same kind of anatomy here. You have the p-n junction, light comes in, you get your little Brownian thing going. And there's some chemistry you do at the top and bottom to try and protect your surfaces and capture charge, but really the bulk of it you can see is made out of silicon. So let's talk about the sun. So this is a really interesting idea, is to ask yourself how much sunlight can you really capture if you put up a solar cell on your house or in the desert. So you imagine, you start by saying, okay, let's say I'm floating out in space and I take a photometer and I point it out at the sun. What is the spectrum of all those photons coming in? So that's the black curve here, and it's called the air mass zero spectrum. So it means you're out in space and there's no air. And that air mass term will make more sense in a minute, so just go with that for now. And you notice it's just this kind of garbled line here. So there's a bunch of spectral absorption going on here inside the corona and whatnot. But overall, you can approximate this as an ideal black body somewhere around the vicinity of about 5 to 6 Kelvin, or 6,000 Kelvin. Probably should be a little bit hotter to match down here, and then the curve should go up. So I probably should have fit it to a slightly warmer body here, but that's the basic idea. It's kind of cool to see that Planck's law works pretty well in practice. So if you add up, you got to look at the units here. So if you look at, it's called the solar irradiance spectrum, and it's watts per square meter per nanometer, right? So what that means is if I integrate over this entire spectrum from 0 up to infinity, I will then get units of watts per square meter, which means if I have a square meter aperture now, collecting all of those photons, I will collect about 1.366 kilowatts in that square meter. Does that kind of make sense? Okay, so then we say, okay, we're not actually in space, right? We are standing here on the Earth, and there's this ocean of air above us that the light has to go through before it reaches our solar cells. And the Earth is also tilted, and we're at different latitudes, say, right? So if in an ideal world, the Earth would be like perfectly perpendicular to the ecliptic of its orbit, right? And then you would be at the equator at noonday staring straight up at the sun, and that would be one air mass above you, right? So directly perpendicular 90 degrees is one mass of air. But then the Earth is kind of tilted, so the sun is mostly over at this angle, right? And if I'm at, say a higher latitude in the US, like we are, then that'll move the sun around some more. Then you kind of have to average all that over the year because the Earth being tilted, you get kind of seasonal variation. So that's where you get this idea of an air mass 1.5, which is kind of just a very crude approximation to saying I'm in the United States and I'm going to sort of average my flux density from the sun at all these different angles, right? So that's why you see this red spectrum here representing the air mass 1.5 or the AM 1.5 spectrum. It's a common phrase you'll see as sort of just the universal standard for the average light insolence you can expect being here in the US. And they even make like the special like test stations where they'll actually have these specially calibrated lamps that will give you one AM 1.5 spectrum by which to measure and calibrate your solar cells. So it's just, you can think of it as a unit of, what do you call it, a measure of performance, I guess. So if I have a solar cell that's kind of specially tuned to this particular spectrum, then I know it will work well in the continental US. So you notice all these weird absorption lines here because of carbon dioxide and water absorption and oxygen and nitrogen. So you get this kind of red spectrum here. You can download the data for that off of the NREL's website, and it's just a tabulated bunch of data for solar light versus wavelength that you can use to your heart's content. So now we have to shift gears a little bit because a solar cell doesn't exactly capture energy per se. A better way to think of it is it captures photons. And it has a very distinct cutoff where any photon that doesn't have enough energy to meet that band gap, it will not be absorbed in your solar cell. So energy is inversely proportional to wavelength, and silicon has a band gap of about, what is it? Did I write that there? It's like 1.1 electron volts, give or take. So you convert that into wavelength, and it's right here around 1120 nanometers. So what that means is all the photons way up here, they don't have enough energy to excite an electron-hole pair, and they may as well just not even exist. You can't capture them. And all the photons down here are the ones we are interested in. So what we do is we take our magic eraser and just erase all that. So this is the total sort of solar spectrum that we care about that is available to us if we have a silicon solar cell. So you notice we converted the units to photons per second per square meter per nanometer. So the idea is if I integrate this from, say, 0 to 1120, and I have a 1 square meter aperture, I will capture exactly 1 times 10 to the 20th photons per second. And then if I add up all of the energy in those photons, I get roughly 800 and plus change watts per square meter. So given a solar cell made of silicon, this is the absolute most physical energy I could, in principle, capture. But then it gets worse than that. So the band gap energy of silicon, 1.1 eV, that's the absolute maximum energy of a photon. Then you integrate over the spectrum. So there's another problem where just because the photon can exceed the band gap, you don't actually capture all that energy. So you kind of imagine a threshold from 0 to 1.1 eV. And I have a photon that's up here at 1.5. So it will excite an electron-hole pair at 1.5 eV. The next question is, what actually happens to them? Do those particles maintain that energy, or what happens to the difference? So have you guys talked about that in this class at all? How many material scientists do we even have in this class? We're about to ask. We got one material scientist. Everybody else electrical engineering? We got electrical engineering. Oh, really? Okay. What's everyone else's background, by the way? Yeah. Mechanical? Ah, okay. So what happens then is, imagine here's like 0 joules. Here's 1.1 electron volts. And a photon comes in and it excites an electron up to 1.5. What actually happens is it immediately falls down to the bottom of its band gap. So that energy difference of the 0.4 eV gets lost to heat, and then it hits this floor where it is less likely to recombine. So what that basically means is all that energy from 1.1 electron volts and above, you can't capture it. It gets lost immediately. You only get to maintain that 1.1 eV. So just because I might have 800 watts plus change of total energy in the photons, you have to truncate them at 1.1 eV, which means at the end of the day, I only have 488.8 watts per square meter that I could, in principle, harvest with a silicon solar cell. Everything else is either the photon just doesn't have enough energy to do anything, or has too much and the difference gets wasted. Then it gets worse than that. So there's some issue with the ability, it's derived from circuit theory. I haven't gone through the actual derivation myself in detail, but it's something to do with the idea of you have this PN junction creating all this photocurrent, and I have to transfer power from a generator to a load, and there's all these kind of source impedance matching issues that you have to deal with. And so what happens is that lowers your 48% down to about 32% there. And so that is now called sort of the Shockley-Queisser limit. So if I have a silicon solar cell and I'm harvesting energy from the sun, the absolute maximum efficiency that's possible in theory is 32%. So that's a little, depressing, but at least there's a lot of energy there.
Was that 32% of the wavelengths that we could consider, or 32% of?
That's 32% of the total energy just landing on your solar cell. So that means if I have 100 watts of just raw solar energy blasting into a solar cell, in principle, the absolute most amount of that I could convert into usable electricity is 32%. So it's a little sad and depressing, but that's just what the physics has given us. So that's why what you were talking about, there's a lot of efficiency issues. It's just because there's, 6, 10, hundreds and millions of megawatts of power landing in the desert. There's only a small fraction of that I could conceivably convert into usable energy. So then, of course, that's the ideal value in principle. So what have people actually been able to do in practice? So, there we go. So this is a solar cell that was in a paper in 1999 where they just kind of pulled out all the stops. And I think in 1999, they were the world record holder for the most efficient solar cell made out of silicon, mind you. There are other materials and other ways to make solar cells, but it was the most efficient silicon solar cell in the world. And I'm sure people have beaten it since then, but if I were to put money on it, they probably haven't beaten it by very much. So this guy came in at about 25%. If you were to go look through the literature today, I'd be very impressed if there's anything more than like 26 or 27. But it makes kind of a nice benchmark to say, what are all the things you have to do in order to maximize your solar cell efficiency? So first and foremost, you have the same outline, and here's just this lump of silicon, and there's a PN junction here, and you got your top and bottom contacts. So immediately you're losing a little bit of energy to reflection off those contacts. So that'll take off a few percent. You have this anti-reflection coating with your surface texturing here, and you try to capture all that energy. Some of it's just going to bounce off of there too. So there's some optical considerations you have to consider. And every time you create an electron-hole pair, maybe they'll recombine, or maybe they'll get to the contacts, or maybe they won't. So you lose a little bit there. And so that's why you can't actually hit the 32% in practice. You hit all these little roadblocks. So one of the key features, though, of this solar cell is its thickness. And this guy came in at 400 microns. And that doesn't really sound like much. It's like 0.4 of a millimeter. But back in the 2000s, that raw silicon required to make the solar cell was actually about half the total cost in the entire integrated device. So that was a big push to say, how can we bring the cost of the solar cell down? Do we really need this giant, huge volume of silicon, or can we cut this, say, in half? So that's where you get this idea of thin film photovoltaics, because just this raw material is such a huge fraction of the total cost. So this kind of brings us to another interesting question, is this was created in a laboratory, but what could you get if you were to just go to Amazon today? So I think this was 2015, 2016 or so. I didn't update it. I think I updated this about 2 years ago. And this is a total integrated solar panel you could buy off of Amazon. And you notice it's 100 watts, or whatever that area is. It's a crystalline silicon solar panel, and it was $1.8 per watt, so it didn't quite meet that dollar per watt threshold. And I did all the calculations based on their specs, and it was about 15% efficient. So then you have this idea of like, okay, I can go through all this effort to create this super efficient silicon solar cell, but who knows what the actual cost was in that. So commercially, they would cut all the corners they could to minimize things, and they came in at about this benchmark, roughly $1 to $2 per watt. So just kind of, these aren't really set in stone numbers. It's just to kind of give you a baseline from which to consider some of the other variations on this. So we'll kind of get back to that in a bit. So why are we not as efficient as we'd like to be? So I kind of touched on this, but this graphic will really break it all down. So you're raining photons in from the sky, and the most obvious problem is you have your metal contacts on the surface, right? So that is just dead space, and that's why if you look at the the metal traces on a solar cell, they look like these really thin interlaced fingers, and they try very hard to keep them as just out of the way as possible, while still kind of covering as much of the surface as they can. So that pretty much guarantees like 1 to 2% loss there, but we can throw that away. Oops, there we go. So you throw that away and imagine I've minimized it. You still have the problem of surface reflection. Just any time light strikes a boundary between one thing and another, some of that light is going to reflect away and some of it's going to transmit through. So how do I minimize surface reflections? Well, I can create an anti-reflective coating, but even that will not be perfect over all wavelengths. You can kind of center it around the center of your spectrum, but you're still going to get some reflection loss off of that as well. But let's suppose that's not a problem. I have a magical anti-reflective coating that's absolutely 100% efficient over the entire solar spectrum. I then have light will transmit through the device and hit the bottom contact. So some of it might get absorbed down here. But if you use something like aluminum, that'll be like 1% loss there as well. So maybe it's not a big deal. Or if I make it out of silver or something, it'll be 99.9% reflection, who knows. But some of the light might just hit the bottom, reflect, and go right back out the top again. So you have this kind of reflective loss where the light goes in, some of it gets absorbed, but it'll just fly right on back again. So what can I do to mitigate that problem? Well, you can just make it thicker, right? So you imagine this like infinitely thick, all that light will go through, and eventually it'll be absorbed, and I don't have to worry about it falling out the top again. But of course, there's issues with that too. Why can't I just make my P layer infinitely forever thick? And I guess the one material scientist in the class might know. And the reason is, when I create an electron, there's only like this finite region here in the p-n junction where electron holes will be created for starters. So somehow you can't quite make that go up forever. Another problem is that I create the electron on the hole, they're going to meander around, and it's just kind of by sheer Brownian motion and diffusion that they make it to the top and bottom. So if I make this really, really thick, did I draw a graphic for that? Yeah. See what's called recombination lengths. So if it's too thick, they just wander around and eventually they recombine after a few microseconds or whatever, and they never make it to your top and bottom. So I can kind of keep going, but I can't do this forever. So you need to strike a balance there. So you have these two competing problems where ideally I'd like this to be infinitely thick so that my light eventually gets absorbed, but I can't go too thick or else just nothing happens there. All the light gets absorbed, but I can't do anything with it. So this brings us to this notion of absorption length. So how do we quantify that idea? So this is a graphic I made a really long time ago. So you define the absorption length as the 1 over E probability for a photon to get absorbed. Photon absorption, it's an exponential function. So as I'm going through a material, the amplitude of my wave will exponentially decrease. And you ask how far do I have to go before that amplitude decreases by 63%. And that's called your absorption length. So I got a crystalline silicon here and a gallium arsenide here, just to kind of show another variation. So you notice now crystalline silicon, its band gap was way out here at 1120. And you see how as you get closer and closer to the band gap, my absorption length skyrockets. And it's a logarithmic scale here. So you notice it's in units of microns. So here's 1/10 of a micron, 1 micron. Here is 10 microns. So I'm out here. And then I can go to 100 microns over here. So you notice I have this trade-off. If I want to capture all my light, I need hundreds of microns, but if I'm too thick, I can't do anything with it, and you have to strike a balance there. You notice also gallium arsenide follows the same thing, but it's a much sharper rise here at the band gap. So the band gap is a little bit lower in wavelength, and I think what you're seeing is this idea of a direct versus indirect band gap. So silicon is an indirect band gap semiconductor, which I believe, don't quote me on that, is why it's sort of a smoother rise up there. Whereas gallium arsenide is a direct band gap, and that's why it's sharper. I think. Someone can correct me on that if I'm wrong, but I believe that's what you're seeing there. So the semiconductors, you want to be thick, but the material is expensive, and you can't go too thick or you lose all this recombination there. So maybe we should just make our solar cells really, really thick. So this is where you get this idea of thin film solar cells. So this was also from Amazon. And you notice this stuff was made out of amorphous silicon. It's thin film stuff, which means probably only a few microns thick. Typically it's like 1 to 2 to 5 per se. So instead of hundreds of microns, 2 microns, right? And there's a lot of advantages to that. For example, instead of manufacturing these giant panels, it kind of comes out of these like sleeves, like paper towels almost, right? So that's one of the analogies people often describe is when you go thin film, you're not really creating solar cells in these integrated systems, you're almost like printing it like newspaper. So the efficiency, of course, goes way, way down, 6% efficient. Part of that's because it's amorphous silicon, not crystalline. But part of that is because it's just so thin. But the cost went way down as well. Before we were at 1.8, now we're at 1.2. So it's less efficient, but it's just so much cheaper to make that you can just make more of it. So that's pretty cool. So what would you rather have? You know, a perfectly 100% efficient solar cell that costs $1 million for every square foot, or would you have this 6% efficiency that costs, you know, maybe $2 or $3 per square foot, right? So we'll just make more of it, and land is cheap, and make a really big solar farm for cheap rather than a small one that's expensive. But of course, the big problem though is thin film is great and it's cheap, but there's so much headroom on my efficiency. I could, in principle, triple the efficiency or quadruple it and still not quite reach that Shockley-Queisser limit. So the problem, as a good way to visualize it, is you imagine some electromagnetic wave coming in from the left, and these are 2 different wavelengths. One is 800 nanometers, or roughly red light. Here's 500 nanometers, which is about green. And I think I put in the actual values for crystalline silicon here. So you notice the short wavelengths attenuate very, very quickly before they would maybe fall out the other end. But the long wavelengths, hardly anything happens. So this is the problem we have to find. How do we compel all these long wavelength photons to stay in that solar cell and get harvested rather than just fly out and never be seen again? So this was a big part of my PhD. It was like, let's just do the math on this and see what happens. So we're not really going to do the math. We're just going to kind of summarize the results of it here. So you remember, here is my solar spectrum here, this black kind of dotted line. And as a very simple baseline model, we just say, okay, here is a crystalline silicon solar cell, nothing at the top, and perfect electrical conductor at the bottom. And again, light is just raining on it from the top at normal incidence. And for kicks and giggles, we'll just make it an even 1 micron thickness. In principle, we could go 2 or 3, but generally 1 to 2 is about what thin films are all about. So that's great because it's nice and cheap. I don't have 400 microns of silicon I have to deal with, so that reduces my material costs there. But somehow I have to compel light to stay inside of this thing before it falls back into space again. So you have light coming in at the top. Some of it immediately reflects off the surface here. Then some will go down, reflect off the bottom, and travel back. And some of it will be absorbed along the way, and some of it will then transmit back out the top again, or it might even reflect back down here and come back up again. So that's kind of an interesting phenomenon, because depending on the wavelength and the thickness, that down and back here might actually destructively interfere with that initial reflection. And you get this kind of weird resonance effect, where you can destructively interfere all of that reflection at once, and all your light kind of gets trapped. So you notice these little peaks and valleys here, where at this wavelength it's actually doing very well. But then you go off that resonance a little bit, and all of a sudden the opposite happens, where this reflection will now constructively interfere, and you get even more reflection. So that's called Fabry-Perot resonance there, and that's what you kind of see in this spectrum here. So you kind of look at this red line. We'll start with the, say, short wavelengths. So the really, really short wavelengths, you get an immediate reflection, and whatever transmits through gets absorbed almost immediately. So that's kind of what you see here. But as you get up to about 500 nanometers and beyond, then the Fabry-Perot effect starts to kick in, because my absorption is not so great. And you see all these little peaks and valleys, and you get this kind of effect. Until finally I get to the really long wavelengths, and almost nothing happens, because I just am not absorbing anything. So you do all the math, I integrate this red curve here, and divide it by this total curve here, and I'm getting about 27% efficiency on my ability to trap light. So that's my light trapping efficiency at the end of the day. So that's a nice little benchmark from which to ask, okay, how can we do better? So let's hop in it. So any questions on that? No, that was a pretty dense sort of discussion there. So if no questions, we'll then say, what's the first thing? Actually, yeah, let's make a little game. What would you do to make this thing more efficient, my light trapping efficiency? No ideas at all?
I have a question. The
Yeah.
Brownian motion, right? It's been a while since I've heard that. That's a random process, right?
Oh, yeah.
Does it have some structure to it?
No, it's just this idea of you have a particle and just kind of at any given moment it might randomly wander in some direction along some gradient. Yeah. So we're ignoring that effect right now. So remember, this is just pure light trapping. On top of that, you have to account for what's called the internal quantum efficiency, which says, okay, now that I've trapped the photon and absorbed it, am I going to actually use it to generate photocurrent or not? So for pure sake of the argument, we're going to assume we have absolutely perfect internal quantum efficiency, and we're limited entirely by our ability to just trap light inside of our solar system. So the most immediate thing to say is, well, how can we just make that go away? So that's what's called an anti-reflective coating. You just add a little thin layer of silicon nitride, and if you ever take 3300, is anybody taking 3300, I hope? You probably did the math on an anti-reflective coating. It's basically like a quarter wave transformer, remember that, only in optics. So it's that idea of some light bouncing around here, and there's a bunch of interference happening where it all constructively interferes in that way, but destructively the other way. You don't get any reflections. So if you add an anti-reflective coating, what happens is we assume an absolutely perfect coating, so there's zero reflections, and it's just light coming down, being absorbed, and going back up again. So we now have this solid black line, what we've done here. So you see how at the short wavelengths, everything's being absorbed, and then it splits right here around 500 nanometers, where now some of that energy is falling back up the top again, because it's not thick enough to absorb it all. And you see as we get way up towards the band gap, it drops way down to zero. But we do come out ahead. You integrate this black spectrum over the dotted here, and you get about 40% of your light trapping efficiency. So what can we do to be better than that? So the next idea is to say, well, does light have to be perfectly perpendicular here? What if there is some magical way I could coax these photons to go that way instead of this way? Because remember, this is a solar panel. It might be, say, a whole square foot or square meter in size. So I have 1 micron of thickness this way, but I might have 1 million microns of thickness in the lateral directions, right? So basically infinite distance. If only I could get light to go these directions. So that's the main, I guess, idea behind light trapping is how do I get light to go from up, down to left, to right? So we do surface texture. So one of the simplest things you can imagine is something on the bottom that just makes it bumpy, so that instead of encountering this perfectly flat specular surface, I get what's called diffuse scattering instead. So if I have a perfect mirror, the ray will hit it and the incidence angles will be perfectly matched. And that's called specular reflection. It's like what happens when you look into a mirror. But when you roughen it, there's some random probability of light bouncing every which way as it hits the surface. And that is incidentally why this looks white and is not a mirror. The only real fundamental difference between a white surface and a mirror is that surface bumpiness. So this idea now, imagine a photon coming in here, some ray, and it scatters every which way. And now just say it scatters off a little bit to the right before it goes out the top. We do some basic trigonometry. This distance from here to here is a little bit longer than that distance there. And so that is called a path length enhancement. It's as if the solar cell were either thicker because the photon has to travel through more of the material before it finally flies off the surface of the solar cell again. So the more I can kind of coax it in these horizontal directions, the more path length enhancement I can expect. So way back in the 80s, some smart guy named Yablonovitch and Cody, they wrote some paper where they said, okay, let's just imagine the absolute perfect amount of diffuse scattering you can get, and put it at the top and bottom of the surface. What would my total path length enhancement be, and how much light could I absorb? So we will derive that in a bit, but it turns out if you do absolutely perfect diffuse scattering at the top and bottom, you get this final curve here, which brings you up to about 81%. So it's pretty close to the 100% light trapping for that given thickness. So not bad. So we're going to now explore this because this is a very common benchmark used in the light trapping literature. Is this notion of the Lambertian limit or the Yablonovitch limit or the Ergotic limit. There's a bunch of different names for it. And incidentally, if you read this paper, it's really, really hard to understand. Because he didn't just trace the rays and do all the trigonometry on it. He did some weird argument based on like the relative density of states inside your dielectric versus outside, and it was really bizarre, and I hated it, so I did kind of my own derivation using just pure ray tracing. So we'll do that because I think it's just intuitive to imagine here's a ray going in, and here's where all the energy goes, and we're just going to calculate the absorption directly. So this idea of light trapping was a big craze for the early to mid-aughts, I guess, the 2000s here. And people were just coming up with all sorts of wacky ideas to trap light. And there was just paper on top of paper just flooding the literature in this stuff. And some of these ideas were smarter than others. The one I really loved was this surface plasmon thing, where they put little gold spheres on the surface of their solar cell. And if they did it just right, some energy would kind of be absorbed at some wavelengths. And this became like a huge craze with this plasmonic nanoparticle trapping of light. But then when you actually kind of just look at it, you're like, you're putting metal on top of your solar cell. How on earth is that helping you? But it took a few years of people thinking really hard about it to realize the obvious. But that was one of the cruxes of my PhD, to say this is not a smart idea. It turns out, you can surface texturing around here is really the way to go. But just for several years, people were just coming up with all sorts of wacky proposals for this stuff. So let's build some intuition. So there was some really obscure textbook I found where he came up with this idea of, it's called the Model-N Slab. You probably won't see it much in the literature, but I thought it was a great just way of visualizing and talking about light trapping. So you imagine here is air with light coming in from the left, and here is some magical material of interest that I care about. We call it a slab, so it's a rectangular slab. And out here is some back contact, could be more air, could be metal or something. And some light comes in and will get absorbed and will either reflect or will transmit through. And I want to kind of talk about the absorption in between. So we imagine we're in a perfect world where there is no reflection here off the front contact. Just light goes in, gets absorbed, and then falls out the back end. And how much of that energy was absorbed? So it makes it very simple. You say the absorption factor, the fraction, is just 1 minus your reflection minus your transmission. So we assume there's no reflection. That's why it's called the Model-N, for no reflection. How original. So you get 1 minus your transmission, right? So it's just very simple. Light comes in, gets absorbed, and flies out again. And then you have some thickness here with an absorption coefficient, alpha, right? So your transmittance out the other end is just this e to the minus alpha w factor here, okay? So this idea then says, okay, given this idealized scenario, I can now talk very intuitively about how thick it is and how much energy will be absorbed. And what our goal is going to be is to talk about big, complicated things as if they were something like this, because it gives a nice sort of intuitive picture in your mind. So you have this notion, it's called an equivalent path length. It says, okay, if I know the absorption factor of that energy in here, I can technically calculate the width after the fact, right? But what that also says is, okay, let's just imagine some arbitrary absorption factor from some complicated system, and say if it were this Model-N slab, it would have some equivalent path length of L. Okay, so does that sort of make sense? This is an idealized thing, but I could generalize it to an arbitrary solar cell and say I have absorbed 50% of my energy, therefore it went through this much equivalent of a Model-N slab. So it's just a nice number to throw at your system to talk about it in terms of more or less path length. So this notion of an equivalent path length is what we care about. So this is kind of an arbitrary, can be complicated, but this is an abstraction on my Model-N slab. So bigger L essentially means more absorption and back and forth. Okay? So now we go back, and so fun fact, you can calculate that equivalent path length for various situations. So for example, if I had this simple 1 micron again, and I put a perfect anti-reflective coating up here, the light will come in, go down, and back again, and I would have an equivalent path length of 2 microns, right? Or what could happen is I don't have that reflective coating, but I have this Fabry-Perot resonance effect, and a whole bunch of light gets absorbed, and that might increase my equivalent path length at a given wavelength. So when you calculate that, it's actually you get 2 times the index of refraction times the thickness. So silicon has an index of refraction of something like, I think it's 3.5, 3.5.
Yeah,
3.5, is that right? 3.4. So the equivalent path length in a Fabry-Perot resonator would be 2 times 3.5 times 1 micron, which is 7. So a Fabry-Perot resonator has an equivalent path length of 7 times 1 micron, 7 microns. Or if I do the opposite, where I'm maximizing my reflection, this is 1 over n effect, right? So it would be 2 over 3.5. So it would be as if it's even smaller than it really is. So it's a nice little metric to say I have a very large path length or a very small path length, and I want to enhance my path length as much as I can using various configurations. So any questions on that? Okay. So then you go to the Lambertian length. We're going to ask now, what is the path length enhancement or the equivalent path length of a perfect Lambertian scattering system? So what you imagine is this infinite slab here. I have perfect anti-reflection coatings at the top and bottom. And light is coming in from the top, and some of it will fall out from the bottom, and it scatters every which way every time it hits each surface. What is the path length enhancement of this system here? Okay? So step 1, you imagine a simple ray, a single photon, say, or a laser beam of light coming in, and it hits the reflective coating here and scatters diffusively into my solar cell. So fun fact, a perfectly diffuse scatterer will dissipate the energy in proportion to the cosine of my angle. Don't ask me to explain why. That's just the way things happen when you have rough, bumpy surfaces and you shine light on them. If it was specular, all the energy would perfectly transmit down through, and you make it perfectly diffuse, it scrambles it every which way. In principle, you could do some weird photonic crystal magic where you have some perfect distribution of rays, but this idea is you have to average that over a whole bunch of wavelengths on that same surface. And sometimes they'll scatter this way or that way, and sometimes they won't. And generally, everything just kind of meanders towards this 4 cosine theta limit here. So this is called the directivity function, which is just sort of the relative proportion of that energy as a function of angle. Okay, so you notice it's a function of theta and phi, because theta is this way, but you also have this phi direction kind of propellering above my head here. So we're looking at just a cross-sectional slice, and you imagine this sort of bubble in 3 dimensions here. But since the light doesn't really care which way the solar cell is oriented, we can just look at this all in a single cross-section. So, okay, let's just ask ourselves, how much of energy does this ray lose, and how much does that one lose, and how much does that lose? We're just going to kind of add them all up. So the total absorption from here to here is this big ugly integral. So you notice it's the relative directivity here times the transmittance, or the absorption, I should say, of that particular ray. So you notice it's this e to the negative alpha w. That represents this length from here to here. And then the secant theta, what does that term represent? Crap. That's the total length here. So w is my thickness here. If I come out over here, it's secant theta, right? So you notice I go to 90 degrees, I get infinity out of that. So that's just and then this is my differential sort of surface area because I'm integrating in polar coordinates. So notice this integral, we're just adding up all the little differential rays of energy from this pass to that pass. So, okay, that's a horrible little integral, but we'll simplify it a bit. So what do we do? First, we're going to assume that our film is very, very thin, right? So if it was very infinitely length, it would be difficult. But if we assume it's thin, then this alpha W term gets very, very small. So we're assuming each little pass up and down we're not losing that much light, which means this exponential term is approximately this here. So there's a little danger here, though, because this secant term wants to go to infinity, but then you weight it by the directivity, and that contribution goes to 0, so it still works. And so you perform the integral, and the total absorption on that first pass is 2 times the absorption coefficient times the thickness of my cell. So basically, it's as if the cell were twice as thick than it really was, just from that first pass from top to bottom. But then it's going to reach the bottom. So imagine one of those rays now hits the bottom, and some of that energy is going to get lost to the environment underneath, and then some of it's going to reflect back up and do the exact same thing again. So now you have this idea of a ray is hitting a surface. What is the fraction of light that leaves down here, which is called the light extraction efficiency, which is what we'll be talking about on Thursday, by the way. So right now, this is the thing we're trying to minimize, is this light extraction. But come in Thursday, and we'll talk about scenarios where we actually care about this particular thing and we want to maximum it. So you can do some math. We're not going to derive that here, but it turns out it's the sine squared of the critical angle determines the total light extraction efficiency. So imagine if I have a very, very thick dielectric with a high index of refraction, very, very little energy will fall out here and the rest will reflect up. But if the index of refraction is very, very low, it's kind of like an impedance matching, and I lose a lot of energy here. So thankfully, silicon has a pretty high index of refraction. 3.5 is relatively large, and you get roughly this 1/n squared factor for my light extraction efficiency here. So all it means is a bunch of energy gets absorbed, and it hits the back, and then this little fraction of it will leave the bottom, and then the rest will then go on out the top again. So then you have the reflection is just kind of 1 minus that, and that should be pretty straightforward. So you notice the total energy reflected here is going to be my total incident energy minus the absorption here. Then you scale that by the light extraction at the bottom again. That tells me how much energy is going to bounce back up here. And then you do some approximations, because remember, this thing is really, really tiny, so it's approximately that. And then you repeat over and over again an infinite series. And this is actually a simple geometric series that you just carry out to infinity and forever. And what you find is my total absorption factor is 2 alpha n squared w. So in other words, my path length enhancement is 2n squared. Okay? And then we do one last little trick where we say, okay, let's say this is a perfect electrical conductor here at the bottom, because we always have back contacts on our solar cells. So I'm not going to lose any light here. I'm only going to kind of lose it up here. It basically doubles my path length from here to there. And finally, we end up at our 4n squared limit here. So that's, you take crystalline silicon, has an index of refraction about 3.5, and you square that, you get something like 9 or 12 or something. You multiply it by 4, and you get roughly 50. So at the end of the day, after all that rigmarole, you find that a crystalline silicon solar cell, if I make it really thin, and I have absolutely perfect diffuse scattering at top and bottom, a 1 micron solar cell will behave as if it were 50 microns thick. That's the upshot of all that. So this big giant derivation, but it's a nice simple result at the end of the day, where you can say, okay, I have an equivalent Model-N slab of 50 microns given a 1 micron slab. That is the absolute most kind of path length I can get out of this sort of solar cell. So if we go back here to this slide, that is where this graph here comes from. It's the 4n squared limit. Okay, so that gives you your 81%. So keep that little value in mind. 81%. Can I do better? Okay, we're getting 81% absorption with a 1 micron slab of silicon. What could I do to maybe trap the remaining 20%? So this is now just sort of the philosophical what if part of the discussion. And I like to do this because this is an experience I've had 100 times throughout my career, where you have this little 20% of efficiency just dangling there. Maybe we can get it, maybe we can't. And people start brainstorming all these wacky ideas, like how can we get that last little bit of energy? So you might be tempted to say, how about something like this? I've got perfect contact, 1 micron thick. I have these little slits here. I'm just going to put a lens up here above my solar cell and focus it all down to that little slit so that it's just going to bounce around inside my solar cell forever. So it's a solar concentrator, right? So people thought about this sort of thing. And the question here is this a good idea or a bad idea? Why would I want to do it? What could go wrong? And I'd like to pose this because you're going to face this sort of weird question throughout your careers 100 times where some pointy-haired boss is going to get some harebrained idea. And you're going to have to tell him, this is great, we could do this, or this is a terrible idea, don't ever speak to this again. So, so say that again? So, okay, that's one question. I have all this, remember, initially I had 1 watt per square meter landing on my solar cell. Now I'm funneling it down to like a little square centimeter point, right? So what was 1 watt or 1 kilowatt over 1 square meter is now 1 kilowatt over, say, a square centimeter. So that's like a factor of 1,000,000 in my intensity. And if you've ever, taken a magnifying lens and burned ants in the sun, you're going to have that problem there, right? So maybe I'll just say, okay, I can tolerate a little bit. I'll open this up some. What are some other problems I might encounter with this? I don't want to burn any holes in my solar cell.
I'm not using the surface area of my cell essentially just like utilizing the.
Sorry, speak up. Wait, what was that?
I'm not utilizing the complete surface area of my cell. I'm just concentrating on a single point. So essentially, it's like instead of a meter square of a solar cell, I'm just having a centimeter square of solar cell.
So, well, in principle, I could have like another lens over here and another lens over here. So, hypothetically, I could get pretty good coverage with my lenses. So let's not worry too much about that, right?
No, I think he was saying
What were
that.
you saying?
Sorry.
What were you saying?
He's confused with the fact that the light eventually does go into the entire bulb, right?
Right, that's what.
That's what you were saying. The absorption decreases exponentially. So even if the light strikes at a single point and it diffuses inside the solar cell, its absorption efficiency further the point where it is lower.
You're saying the absorption efficiency is lower? Why would it be lower?
I was just explaining to what
Oh,
I'm saying.
because it's just going to bounce around here forever, right? I just need to get it into the solar cell. And I got a perfect contact here, so it's just going to bounce around. And I might lose a little bit out of these guys. Maybe I can tolerate that. So maybe those aren't deal breakers necessarily, unless you've got any other ideas.
Ones need to track the sun.
Yes. What if the sun is not right here, but over here slightly? What will happen then? All the light will then bounce off of here and never touch my thing. So now I have to track the sun. Whereas before, it didn't really matter which direction the light was coming from. I didn't have to perfectly align everything. This now I have to point at the sun. So now I need tracking, which is big and clunky and expensive. And I got this giant heavy thing in front here that kind of has to be dealt with maybe. So that might add a little bit of cost, right? Any other wild ideas? So here's the first problem I wrote down. I have all these heavy mechanical fixtures, and I have to track the sun with all this, right? And do you think that's like a 10% increase in my cost, or it's a 50% or 500% increase to have to track the sun now? I don't know, but it's going to be a lot. So this is what you also said. Alignment's going to be a big deal, because if the sun's off, then my focal point will move, and I'll miss my little target. So that's a big, huge problem. But let's also remember, I'm already getting 80% with this configuration here. So if it's any more than 20% more expensive to implement, I've gained nothing. So let's go, if it were 30% more cost just to capture 20% more light, there's no point. I came out behind. So there's this idea you'll hear from time to time, I'm chasing pennies at the expense of dollars, right? And this is something that will happen a lot, where just because it looks like it might work, there's all these other little factors and variables you have to think about in the big picture. that have to be weighed for. So this idea of like, yes, in principle, I might get absolutely like 98% light trapping, but now the cost has gone way up, and all it gave me was an extra 20% boost in my efficiency. What if I just, instead of being 1 micron, what if I just made it 2 microns, right? Then that might push this from 80 to like 85 or 90 or something for all you know, right? So there's simple solutions to get what you want, and then there's big, horrible, complicated ways to go about it. And that's kind of the take-home lesson that I like to close with, because it's not like an absolute set-in-stone sort of solution, but it's an interesting idea. It's simple and it's efficient, and just because you can do better doesn't mean you should try it or that will be cost-effective at the end of the day. And this is this is something that will happen time and time again. I promise. You're going to be working on some project. You're going to be trying to solve a problem. Some guy will come along with some harebrained idea, and it might be brilliant, or it might be this sort of thing where just because it kind of sounds good on paper, it's really not. That's why you generally don't see that sort of thing. So any big questions before we close? Yeah.
I have a question. So, well, maybe kind of a question with more, maybe you can help me understand this a little bit better.
Yeah.
So, I see 3 problems with this. You have 1 is the light trapping, the reflections. 2 is the band gap using a specific material, right?
Yeah.
And the 3rd is the circuit analysis with transformations and everything, right? We lose a little power there.
Mm-hmm.
So you think that there's a bigger like efficiency gain in light trapping versus the other 2? Or do you think
that is a good question.
I know you said that the materials outside of silicon are really expensive, so maybe we're not gaining that much off of the band gap.
So we'll
Maybe there's
way
things
back
that I
here.
don't understand about the circuit, transformations or whatever, but
So I think it was, where are we? This slide here, yeah. So hypothetically, I don't have to use silicon. There are other materials you can use to make solar cells. Again, if you talk to, I think Mike Scarpola, he's doing CZTS, copper, zinc, tin sulfide, to try and make solar cells because they're presumably easier to manufacture and they're cheaper. And maybe they have a better band gap, or maybe they don't. You'll see this sort of thing maybe on like a Mars rover, where space is a premium, right? And you need to squeeze every last drop of efficiency out of your solar cell that you can. So they won't necessarily be satisfied with a silicon solar cell. They're more than happy to drop an extra $1 million on some like gallium arsenide solar cell instead, because instead of being say 32%, it might go up to 40%. And so then that, and every last watt you can get out of that solar panel is important. There's other stuff like dual band gap semiconductors. I have no idea how that really works, but it's the idea of you have one band gap for kind of the short wavelength photons, then another band gap for the long wavelengths to try and capture more of that internal efficiency as well. So those are all interesting ideas, but the question, you still have to play that good idea, bad idea problem in your mind, where is this something I can implement cheaply enough so that people will put on their homes? Or is space a concern, like it is when you're on the space station, and weight is a big problem, so I can't just bring an acre of solar cells up into space, in which case they probably will pull out all the stops and go after some kind of solution like that. So there's a question of what's most important to you and what are you willing to spend on it. So for this class, since it's optics for energy, I kind of limit it to the scope of like, the power grid, in which case, cost is everything. But in principle, you could be building a space station or a Mars rover or something, and now you've got a blank check and you care about maximizing that number there to as much as you possibly can. In which case, there are a lot of little magical tricks you can do to increase your efficiency. So that is a very good comment. I should just contextualize there. We started with silicon and we stuck with it for that context, but we didn't have to do that. Any other questions?
No.
If not, then you're all free to go.
Yeah,
So I hope you had a
we
good
will
time.
have James back on Thursday to talk about light extraction. And let's thank him one. Stop the recording.